Hey guys, welcome to the video. I'm Dex and you are in the engine room. I teach data engineering on this channel and I am demonstrating the concepts and the design patterns behind data engineering by building out an actual ETL data pipeline, a very simple one. We're taking source data from a flat file, a CSV flat file, and we're ultimately going to land it in a relational database. So we're almost to the end of that process. We've demonstrated, extracting data from the file, doing implicit transforms on that data using Xfile, which is one of the data engineering tools that I've written to help me do my job better. We had a side quest where we built a data filtering front-end tool that we could bolt onto our pipeline so we can screen out bad records. And we're just about ready now to take the output from that phase, okay, and land it in a database. That is a heavy enough lift compared to the other things we've done that I thought it should be a two-part session. So in this first session, I'm going to do an explainer about databases, kind of dig a little bit deeper, and then take you behind the scenes on a little piece of automation that I've been working on that is relevant to this next phase. Okay, so let's start by talking about databases a bit. Most of the world's business data is stored in relational database management systems, RDBMSs, right? And it's useful to know the history of these things. Where do they come from? Well, they came from, like a lot of the things in our industry that are interesting, they came from IBM. So in 1970, a guy named Edgar Codd, who was a programmer for IBM, came up with a theoretical system that he called relational theory. Relational theory was, or is, a cousin of set theory. And as a kind of a theoretical basis for how to structure data in databases, it was pretty powerful because given that it's related to set theory, and set theory is a mathematical theory, it meant that you were at least within striking distance of being able to reason about your database and what's in it and how to retrieve that data. You're able to reason about those things using formal methods. In other words, using things that are like mathematical proofs. And that's good, okay, if you're in a business where correctness matters a lot, right? And where you have to design these things and verify their correctness. Now, IBM wasn't that interested in relational theory at the time, so this sat on the shelf for a little bit, but E.F. Codd kept pushing behind the scenes. And meanwhile, in 1973, I believe it was, two other guys who worked at IBM, who were also interested in these relational databases, this new relational database technology, Chamberlain and Boyce came out with structured query language. Okay, this was a language that you could use to talk to relational databases. Now, again, at this time, the business landscape wasn't like it was now. There was a lot of fragmentation in terms of databases. So business X might have one database that was structured in one way, and there was no real common thread as there is now between designs of how databases were structured, as it is now. If you understand SQL, and you understand the basis of relational databases, you can go to a firm that's running Oracle and you can kind of understand more or less what they're doing. If you go to another firm and they're running Postgres or MySQL, you kind of more or less understand what they're doing. That wasn't necessarily the case back then. And again, IBM was not, when Codd came out with his paper, they were not really into relational databases at all. That came later. So relational theory in 1970, SQL in 1973, and then this thing started to catch on. And then sometime later, it caught on so well, people began copying the relational database design and doing it so poorly that Boyce and E.F. Codd himself felt compelled to come out with what they called B, C, and F, Boyce Codd normal form. These were 12 rules, just like Dr. Peterson. There are 12 rules for structuring data in a relational database. And we talk about this colloquially as normalization. Typo. Okay. So there are 12 normal forms, 12 rules in BCNF. And the idea is that when you design a relational database, what you're usually trying to do is align that design as much as possible with these normal forms. And if you do, the idea is that you reap more of the benefits of storing data in and retrieving data from a relational database. Okay. Now that's true much of the time. Sometimes you want to go in the opposite direction. And the reason I'm talking about that is because we are building, in a way, data engineering as a craft. One of the things it does is it bridges the gap between the part of the business where you really want to try to follow BCNF, you really want to try to normalize databases as much as possible, and a part of the business where it's actually in your interest to denormalize databases to a certain extent to make life easier. Again, data engineers have to understand both sides. So let's talk about the first side first. Right? So again, we're talking about relational databases, and of the business data, of the relational databases that exist in the world, they roughly fall into two families. The first family is online transaction processing databases. Okay, so when you go to reserve a rental car or hotel room or a seat on an airline or what have you, most of the time, whatever you do online or with your mobile app or anything like that, it ends up in a database that is an OLTP database. Same thing with online e-commerce. Let's take e-commerce, right? So you have an online e-commerce database, and it's designed for online transaction processing. Now, why is the normalization system important? Because, for example, one of the things you have to do, aside from erase spurious lines, you've got to capture business events. OLTP databases are optimized for capturing business events where there are lots of small reads and writes, and your data is subject to updates. Okay. So let's take a look at, let me illustrate this with a counterexample. Here's how not to design an OLTP database table. So you have an ID. So this is your customers table, let's say. And you figure that to save on space, you're going to have customers and all their actual order information in the same table, right? So you've got an ID because every record in a relational database has to have a primary key. You have a first name column, okay? You have a last name column. You have an address column. You have an email column. You have an order ID column, right? Because they're ordering something, and each order that someone places has to have a unique ID. And then you have a SKU ID, let's say, stock keeping unit, right? You have the actual catalog ID of the thing that they're ordering. Okay. So now, if you have one customer, okay, fine, that person has a first name, last name, they live someplace, they have an email address, they place an order, and they buy something. Now, what happens in your e-commerce system if that same person orders 5 items? or 10 items. Well, then you have to repeat first name, last name, address, email, order ID 5 times or 10 times or n times for however many times, however many items are in that order. Only the SKU will be different, okay? Because they're ordering, let's say, 5 different SKUs or 10 different SKUs. Now, what's the problem here? Well, there are a few problems here. One is that you're doing an awful lot of writing to your disk, okay? And that's a problem in terms of power consumption. It's a power in terms of wear and tear on your hardware. You're doing a lot of writes to storage. But the wear and tear thing applies whether you're using spinning disk, as was common back in the day, or solid state drives, because even solid state hard drives they are rated for a certain number of read write cycles, okay, on those logic gates. And when you exceed that number of read write cycles, you're either going to retire that drive, or your error rates are going to start to exceed specifications. So that's a problem. The other problem is that if this customer changes their email address, now if they've ordered 100 things, for example, okay, then you have to go and change this record 100 times. Okay, you have to change this in 100 places. And that goes for any other thing. If they move and if they change their email address, now you're changing all these records that already exist. Now, sometimes you have to do an update, but you shouldn't be repeating yourself, okay, if you don't have to. And the fact is that database normalization sets up an environment where you don't have to, right? So in the way we typically use relational databases for online transaction processing, what we instead say is we have a customer table. And in the customers table, there's, the ID, the first name, the last name, and so on, okay? And then we have an orders table, right? And in the orders table, there's an ID, and then there's a customer ID. And this here is a value that points back to this table. It's what's called a foreign key. And so these tables are related to each other based on the value of the foreign key. So we can connect these when it's time to query things. And then you might have some aspect of the order, and then you're going to have another table called order items. I'm going to break it out that way, where what you have is you have a foreign key that points to a specific order, right? And then you have another key that points to your actual catalog table, right? So that if John Smith, okay, places an order, there's one row in customers for John Smith. There's one row in orders for John Smith for that specific order. And then there are 5 rows in order items for every item that this customer ordered, okay? And if we have to change John Smith's email address, we change it in one place here. And that's it. And that's a very good thing, okay? And then when it comes time to go back, once he's gone online and placed that order, and we've done these inserts to these tables to register the fact that he filled his shopping cart and clicked submit on the web page, then the fulfillment side can go and query these tables out and say, okay, what did John Smith order? Okay, let's go pull those from stock and put them in a box and ship them out the door. Okay, so that's OLTP, and that goes for e-commerce, it goes for hotels, the vast majority of business data in the world is stored in databases like this. Okay, now there's another design pattern that is used under a different set of circumstances. So again, this is online transaction processing. This is things that are happening right now as your business is running. But there's another side of your business where you're looking at what has happened. What did we do last quarter? What did we do last month? And we're asking analytical questions as opposed to operational questions. Okay, and that type of the databases that support that kind of operation, those databases can still be relational, but they're built according to a different rule set. Those are online analytical processing databases. And most of them are built using a specific design called a star schema. All right? And what's a star schema? Well, it's a schema that looks like a star. Okay, it's a way of arranging your tables and defining the relationships between them. So in OLTP databases, remember, we're trying to avoid, we're trying to eliminate unnecessary repetition, okay? Because why? Because if you have to change something, you end up having to change things in multiple places. But with star schema, with OLAP databases, we don't care about repetition. Why? Because this is an analytical database. It's meant to be retrospective. No one's going to change anything in this database. This represents things that have already happened, and all we want to do is ask, almost, you could say, we're ask forensic questions about what went on. So the center of the star schema is called a fact table, right? And the fact represents something that has happened in your business. Someone bought something. Someone subscribed to your service. You know, whatever the business fact that you're interested in, right? Something happening, Dave, and you want to ask questions about it. How many times did it happen within a certain time window? What are the most common attributes of this fact? Now, the attributes of a fact in OLAP schema are represented by what are called dimension tables. Sometimes we just call them dim tables, okay? And the idea behind a dim table is it represents some attribute of the fact, but usually it's an enumerable attribute, or it has a cardinality. There's a certain number of them. For example, the name of a customer would not be a dimension, okay? Because there's an essentially unlimited number of names. But things like month, the month in which this sale happened, if we're talking about a sales fact, right? That would be a dim table because there's only 12 of them, only 12 months. And literally what you would do is to prepare this table, you would go and you would write 12 records into this dim table, and then you never update it again, okay? If this is, for example, this is a dim, let's say this is the state from which the order was placed or to which the order was shipped, okay? Then there would be 50 records in this table, and you'd initialize that once when you set up your database and leave it alone. So any of those type of enumerable attributes of the business fact go into your dim tables. And then what your fact ends up being, a record in your fact table, is mostly a collection of foreign keys to the different dimension tables. And that's very different from this system where we have this kind of like a parent-child-grandchild relationship where the foreign keys all, point in this kind of upstream cascade, which can be significant. Here, there are foreign key relationships, but they're at most one table deep. Now, why does this matter? Because here, it's relatively easy to simply find out who ordered what. John Smith made he placed an order on this day and he ordered these things. But now if you want to say, well, how many of the things that John Smith ordered between, October and December were in this category of things in our order, in our items catalog? And imagine we're joining to another table here, which represents items and there's categories and what have you. So now we're talking about a significant number of joins. Okay. And remember, joins impose a computational cost on us. They're not free. And as you have more and deeper joins, your query performance starts to degrade. Okay. So those kinds of analytical questions, right? Like how many people who live in this zip code or who have this area code, order items with that fall into a certain category in the summer months. Okay. Now here, okay, if you say, for example, let's say you're looking at a given sales channel. Well, the fact is that there's a limited number of zip codes in the New York sales region, right? So this can be a dimension table, and you simply write out all the zip codes in your given sales area to this table, right? And you have a dimension that's month, right? So now when you ingest records into this schema, into this table structure, John Smith goes in here. Each order goes into the fact table. And if John Smith ordered two things placed two separate orders in a given month, then there's two records in here. And all the John Smith info repeats, because we don't care about repeating records, because we're never going to change this. This has happened. No one's going to update this, right? It's an accomplished fact. But now, so with that, we can now start to say, okay, how many orders were placed where the zip code was this and the month was this. So you're still doing database joins, table joins across these things. But because the joins are only one table deep, your performance can be very good. All these tables are indexed. All the dim tables are typically indexed. So looking up values is very fast in them. And this is a very, very, very effective design pattern for those kinds of questions. So that's the difference between OLAP and OLTP. And again, most of the time when you are building a data pipeline, assuming that you're landing data in a relational database that is meant to be an analytics database, very much of the time, this is what you're doing. You're landing data in a star schema. So that's kind of why, data engineers have to know both sides, right? They have to understand the design intent of the database, where the data is coming from, and they have to understand the ways in which they're essentially going to reshuffle data and break the normal forms, okay, in order to get it into a form where the analysts have an easy time asking the questions, really answering the questions that they're interested in. So that's a basic explainer for OLAP and OLTP. So next, we want to talk about an actual data model, the data model that we're going to use for our database. We are pulling data, fictional subscriber data, from a CSV file. We assume that CSV file was dumped from an actual live business database, okay? And here's what our target data model looks like, okay? So this is just a data model that I've worked up in what's called an ER tool, or a case tool, computer-aided software engineering. And this is actually where we're going to land the data in our data pipeline. Now, we have a fact table, right? Subscription events, because if you remember from the previous videos, all the CSV data that we've been wrangling has been related to, subscribers to some fictional subscription-based service, okay? And you notice here, we have all the actual subscriber information, right? First name, last name, email, okay? And that stuff can repeat. That's perfectly fine, because once it lands here, this is never going to change. And then we have some interesting things here. Now, you remember that in our, actually, let me pull that screen up momentarily. So let's take a look. Yeah, there we go. So if we look at our source data, we notice that we have status values, right, for each customer. Okay. Now, here in our data model, what we have is an event type ID. Okay. Why? because we're trying to get a little bit more granular in terms of how we analyze the stream of events. We can look at the lifetime of a customer in our system as a series of events, as a series of facts, as a series of things that happened, right? And so what happens, like, if we say that Johnny Walker subscribed, his sign up date was 12/02/2019, okay? Then what that means is that we would insert a record into this table where this matched his name, first name, last name, email, and the event type was, let's say, subscription start, right? And then his subscription also expired on 12/02. Oh, actually, I'm sorry. This is a one in the future. So there's actually no more events for him. He subscribed and that's it, right? But if we have someone else whose subscription expired in the past, then we essentially have two events for this person. So, it's kind of weird. We're taking this one user, this one entity in our data, and we're splitting him into two records in our fact table because there are two things that happened. This person started a subscription on March 1st, 2018, and this person's subscription expired on 2019. And what that means is that there was a start type event, okay, on a certain date, and there was an end type event on a different date, because again, these are subscription events. And then what we also notice is that I think I'm going to update this model to include the original raw date just verbatim in the fact line. But I'm also going to break out the date so that I'm going to break out the event type, of course, but also the year, just the year. I'm going to break out the day, okay? Because think about it again. These are things that have a finite cardinality. There's only so many of them. There's right, in this case, even though you could say there's an infinite number of years, it's really not. We're going to start from, let's say, I don't know, whatever year we started the business to, I don't know, 100 years in the future or 1,000 or what have you, right? So year, day, there's only 365 of them in a year, right? 12 records here, okay, and 7 records here. And then so then we'll be able to ask questions like, what's the month in which we tend to get the most subscriptions, right? Because you're just counting up the number of events where the month ID points to a specific month. And then you can start to run numbers, and you can ask all these interesting analytical questions about your data just because you've transformed it in a certain way and dropped it into this schema, which again, would be a terrible schema for actually trying to run a day-to-day business. This is a schema for analyzing what your day-to-day business has already done, how it has performed. And it's pretty stellar, in that respect. So this is where the rubber is going to meet the road. Well, in the next episode, we'll actually point this at a live Postgres database in my data center. And we're going to basically blow these tables into that database. And then we'll turn around from our code and start to, and connect to the database and start to push records into it. Now, this brings us to the other part of this, this explainer, which is the automation that I've been working on. So, I often have to, spin up OLAP schemas, as you can imagine. And typically, I just end up writing a script to populate things like dimension tables of different kinds. And as I was kind of making this video series, I was kind of dreading having to go in like the drudgery of doing these scripts. And it's like, well, why am I dreading this? I should write a tool. So I started writing a tool, right? And it's called degenerate, right? Dimension generate. It's a dimension table generator. And what it does is it generates SQL insert statements, or it can generate just lines that you can dump into a CSV file that you can use to populate these dimension tables. So, and I got almost all the way through it. And then I said, I should back out some of this work and just kind of do a ride along with the for the YouTube channel, so that whoever wants to watch can see what what I'm doing here, or what I've done so far. So let's walk through this a bit, because this I think it can be useful. So again, back to my same old patterns, right? I use Docopt for just about everything, as far as command line utilities are concerned. So this usage string tells us that there's a plugin module. This is the thing I started to add, and then I paused and said, I should do a video. So this is the plugin module, which ultimately is going to make this a really useful tool for someone other than me, because someone else will be able to come in, point this at a Python module that has their code in it, and adapt this to work for their applications. But disregarding this for just a moment, we have two different modes, right? SQL mode and CSV mode. And in SQL mode, it's going to generate a SQL statement that deals with a specific table that's in a schema that you've specified. It's going to generate some number of tables, excuse me, some number of columns. That number will be very small, because usually, dim tables are very narrow. They have usually only 1 or 2, maybe max 3 columns. But this doesn't care. Just say what the columns are. And for testing, there's a limit switch, right? So if you're generating data for a table that's for a dim table that's going to have a lot of records, like a few hundred or a few thousand records, you just want to test out what you're doing. You can just set a very low limit and just tweak it until you're satisfied, then run to completion. Okay, so what's going on here? Let's start from the main and work backwards, right? Actually, well, better yet, let's actually run this thing. So it's like degenerate, right? Get the usage string. Now you say degenerate -- plugin module foo, because it's ignoring that for right now, or it should be --csv -- delimiter, right? Because remember, you're generating CSV data, right? And so let's say we're going to use the pipe, and then actually that's it. There we go. Okay, so I could literally say, I could just run that, and then like, for input.csv, and I can just boom, and now that I've got that file ready to go. I can copy it. If I'm using Redshift, I can copy it up to an S3 bucket if I'm on AWS, and issue a copy command where it'll just, the database will ingest this whole thing in bulk into a table. Or I can do it in SQL mode, where I'm literally just generating a series of insert statements, right? So for example, if I were to say plugin module foo, but I would say SQL mode instead, and then I were to say schema public table my dim, right? I'm sorry, that's a dim table, right? Dimension table is my dimension, right? And then, well, actually we're using weekdays, right? So let's just say dim weekday, right? And then you'd say -- columns, and you'd say ID and day, let's say, right? And there we go, okay? Insert into public, that's the schema, right? Table, dim weekday, and then you have a little values line here, a columns line, I should say, and then the actual values, okay? So that's kind of all right. I kind of like that. That's a good first approximation. And so what I was working on when I paused was, so if you look here, what's going on here? Well, we spin up, right? I just added this a little while ago, okay? But essentially, we were using Jinja 2, okay, which is a template, a Python templating library. And let's say in either mode, what we're going to do is we're going to call a Python generator function, right? And that's going to return a series of arrays to us, okay? And then for each array that we get back, we're going to use that array to populate the right kind of template. And all right, so for example, so this is a line array generator, right? So you can see that all it's doing is it's actually returning an array with, right, with the primary key of the table and the actual value. Now, I think I changed this to weekdays, and I didn't change the thing. This is actually, now it's, the initial kind of naive demo just had like the first 10 letters of the alphabet, so it was letters, but now it's like, okay, data, right? Okay, so that's that. We have a CSV line template, an SQL value list template, and an insert statement template. But you get the idea. This is it's a generalized way of spitting out data that you can then use to populate a database table. So what I am doing now is I'm switching over from a hard-coded line array generator function, okay, to something that I can plug in, right? Because it doesn't make much sense to just have to, every time I want to use this tool, you know, even from one dimension table to another, if I'm generating, you know, dim weekdays, you know, and then I go to, you know, dim month or dim year, whatever. Now I have to go and rewrite that piece of code. I don't want to do that. So what I'm doing now is I'm switching over to a plugin model, which is common across just about all the data engineering tools I write, where I can, where you can basically say, plugin module, and you pass it the name of a Python module. And then it's going to load a line array generator function, just like this one, but external from that module. And then run it the same way. So for example, if we do, and I think I actually just about got it done. Let's see. So let's do touch weekday generator dot py, okay? And then we say, cut, right? And then we say weekday generator, right? So that's it. Okay. All right. So now, okay, this is good because now we'll pay attention to the plugin module parameter that we pass as an argument. We will no longer refer explicitly to some internal line array generator function. We'll be looking at, you know, what the line, and for right now, we'll just say that you have to call it line array generator. I think I'm going to change that when I add the options to load a config file instead, because with a config file, you could specify one Python module that has a bunch of different line array generators. They're all named something, but they're all in one file. And just like I do in X file, I can have like a rule set that just like, okay, for this job, for this generator job, point that to that and what have you. But for now, we'll just, you know, so let's see. I think we're just about good because what we're doing here is I commented this out. Let's comment that back in. Okay, so that's my line array generator function. I'm going to load that from the plugin module, which I've passed on the command line. And then I'm going to say, actually, come to think of it, do I have a, yeah. If I remove that, nothing else should have to change. Okay. Line array generator. Yeah. Yeah. Okay. Let's give that a shot. Right? So this should work the same way that my CSV, right? Okay, well, actually now it should give me an error because I'm referring to a bogus plugin module. Let's see if I get a good error. Okay, good. That's a good error, right? That makes sense. Now, where is my actual weekday generator, right? My weekday generator is here, and here's my line array generator function. So now I want to point it to the wrong, yeah, I want to do this. Let's do that. Good. And now, so I want to say plugin module month generator, right? Okay, good. That's good. Okay. Now let's point it at weekday generator. Weekday generator. There we go. Okay. Now, let's see. Oh, but I did something wrong there because, yeah, I broke something because this is supposed to be, yeah, this is supposed to be just one Monday. So let's see. No, still not working. So I'm gonna play around with that some more until I find that bug. It's probably something silly I'm doing because I had it working not that long ago. So so that's what I'm working on, and you can see that again. This is a very tiny thing. It's like I'm automating something that's just toilsome. It's not rocket science. It's not any big deal. But again, I really very strongly believe in kind of getting those small wins and getting it by making, you know, the smallest, sharpest tools possible, and then bolting them together into complex things that do cool stuff. So this is that's degenerate. I'm gonna finish this out, and then I'm not gonna add any actual database connectivity logic to this at all. This just generates either CSV or straight SQL. And in the case it generates SQL, same thing. I'm not going to have anything logging into the database. I don't need to. I can pipe that SQL into some other command that actually already exists to run SQL against a remote database. So I'm keeping this tool as simple as possible. I don't have to worry about credentials, anything like that. And you know, the smaller it is, the shorter it is, the easier it is to kind of debug and reason about. So anyway, this has been, I see I'm at the 3/4 of an hour mark. So this is probably a good stopping point for this video. We've talked about relational databases. We've talked about the two main kind of patterns that govern how we design and build relational databases, online transaction processing and online analytical processing. For our purposes, in terms of our target, where we're going with the data, for data engineers, it's almost always an online analytical processing database. But it behooves us to kind of understand that our data is almost always coming from an online transaction processing database, and understanding kind of the design intent of that source is going to help us, you know, as we talk to our stakeholders and figure out, you know, how to get them the answers that they're looking for, okay, from the analytics database that we're building and populating for them. All right. So in the next episode, we're going to push ahead. We'll connect to my Postgres database. We'll push this model here, this data model into that database, and then we'll start populating it using the tool from Mercury that I've mentioned a couple times. That tool is called ngst, and essentially this kind of wraps the functionality of connecting to a remote data store and then receiving records and forwarding them to that data store in a user-defined way. That's all that is. And so it's a relatively simple thing. But then when we hitch this up to Xfile, then hitch that up to, you know, and kind of snap on our filtering tool, then we've got something that's pretty neat, and it kind of fully demonstrates almost the very simplest example of what it is that data engineers do for a living. All right. So thank you for watching, and please like and subscribe if you thought this was helpful. All the relevant links are going to be in the description, and I'll see you all next time in the engine room. Take care. Sometimes I am so stupid I can barely stand myself. Let's give that a shot now. That's much better. Let's see, month generator. Let's go back to day generator, no, weekday generator. There we go. See you next time.